All right, geometry students, today we're going to get the final portion of Unit 4 cleared up. Now, there's not a whole lot of information left, just a couple of special cases that exist with isosceles triangles and also some more special cases inside of triangles, but this information just did not fit with either of the first two portions of the unit that we looked at, and also there was just already enough information in those two portions. So this is what remains. So we're looking at the structure of isosceles triangles. Now, generally speaking, of course, what we said is that the term isosceles simply means at least two sides are going to be the same. Now, that term is not specific to triangles only. It can apply to any shapes. However, typically the only shape that we really run into that uses the term isosceles is trapezoid. They like to use isosceles trapezoids when trapezoids do appear on our tests. Okay, but the word simply means at least two sides that are congruent, and that could apply to just about anything. Now, different vocabulary goes along with the idea of an isosceles triangle, and we catch a lot of special cases inside, a lot of special properties inside of isosceles triangles, so it's important to get a good grasp on the vocabulary. Now, the two sides that are congruent to each other in the isosceles triangle are what we call the legs of the triangle, and the one side that is unique is referred to as the base of the triangle. And of course, as we've said several times throughout our travels in geometry, being a base has absolutely nothing to do with being on the bottom, nor does height have anything to do with being up and down. These locations could be anywhere in the figure, so it's important to understand the definition so you know what conditions you are looking for in the problem, not just what positions in the problem. Okay, the location where the two legs of the isosceles triangle join together is what we refer to as the vertex of the triangle. Now, it's an unfortunate naming situation, as we said when we were going through Unit 4, because all of the three locations where the sides of the triangle join together, those are referred to as vertices. So there are three vertices inside of an isosceles triangle. However, if a problem refers to the vertex of the triangle, then that is the one location where the two legs join together. Okay, so an important distinction between the term vertices or the vertex. Once you have located the vertex, there is an angle at that particular location, and that is what we refer to as the vertex angle. The vertex angle is positioned between the two legs of the triangle, and that leaves us two other angles in the triangle that are connected to the base of the isosceles triangle, and those are called the base angles. So again, please keep in mind that vertex does not mean top, as some of you might think it means, and base does not mean bottom, as some of you might think it means. Those are simply angle locations that are connected to particular properties in the triangle. So look for those properties, not just the positions. Okay. Now, we'd already talked about that there was a connection between the side lengths and the angle measurements in a triangle, and that connection would be that the largest side length and the largest angle measurement are always across from each other in the triangle, and so forth with the smallest angle and the smallest side in the triangle, always across from each other. What this means is that if you have a tie in your triangle for side lengths, like we do in an isosceles triangle, that means you're also going to have a tie on two of your angle measurements that are across from those two side lengths. Okay, so that's an important property to keep in mind. They do like to put that one in play when they are having you solve for missing information in the triangle. So remember, two side lengths the same, it means two angle measurements are going to be the same. Okay, and that's going to probably unlock your problem for you. Okay, the next thing, or the last thing actually, we looked at in Unit 4, Unit 4 was finally over at this point, was special segments inside of triangles. And there's a lot of information in here, and some of it does deal with isosceles triangles again. But just generically speaking, we come up with some new vocabulary. Okay, the term altitude refers to if you connect a point in a triangle to the side that is across from that point in the triangle, such that this connection forms a right angle. That is what we call an altitude, or what is more informally referred to as a height. Okay, so altitude is the official word, height is kind of the informal word, but they tend to mean the same thing. If you move perpendicularly away from a side length that we're usually calling the base, how far is it to get to the vertex across from that? And as you can see inside of our triangles here, it is possible that your altitude or your height might actually be a measurement interior to the triangle, and depending on how the triangle is structured, like the isosceles triangle on the right, your height actually might be a measurement that exists outside of the triangle. But in either case, okay, it is a measurement that forms a right angle with the opposite side. Median, okay, is what happens when you connect that vertex to a side opposite, just like we did with the altitude, but this time we're not worried about it forming a right angle. This time we're worried about it connecting like a midpoint. It's going to bisect the side that it intersects with. That is what's called a median. Okay. Angle bisector is a term that we have seen before this year, and of course an angle bisector is going to chop an angle in half. So just like the other two examples that we've looked at so far, we're connecting a vertex to the side that is across from it in the triangle, only this one is worried about bisecting the angle that it is coming from. Okay, and then we run into this one from time to time, not as much as the other three. That's what we call a perpendicular bisector. As you can see, it is bisecting the side that it is coming from. Okay, and it is perpendicular to the side it's coming from, but the opposite side of the perpendicular bisector is no longer concerned with trying to reach out and make contact with that vertex that is on the opposite side of the triangle. Okay, so it's just perpendicular to a side length, so it's like a median, and it's like an altitude in the sense that it's trying to be perpendicular, but it will not actually make contact with that vertex that is across from it. Now, the thing that became special about this, and the reason why we talked about these four terms after such a long discussion about triangles and then into isosceles triangles, is this. Pardon me. If you were to take an isosceles triangle, and that's what I did, I took the exact same isosceles triangle 4 times here, and I installed an altitude into it, and I installed a median into the second one, and I installed an angle bisector into the third one, and a perpendicular bisector into the fourth one. Okay, and these measurements are all accurate. Okay, so everywhere that there's tick marks, those lengths are exactly identical. Where there's angle measurements, those angles are exactly identical. And I took all 4 of these triangles and I copied them and I pasted them and overlaid them on top of each other. And as you can see right there, there is absolutely no difference between the triangles or the 4 line segments that were in the middle of the triangle. So the short end of that is if your triangle is isosceles, the median, the altitude, the angle bisector, and the perpendicular bisector, they are all the same line segment. Okay, and that's going to be important, because what that means is if you have an isosceles triangle and you discover any of those 4, just a median or just an altitude or just an angle bisector or just a perpendicular bisector, that will mean that the properties of all 4 of them will apply if the triangle is isosceles. And that is important. When they do introduce an isosceles triangle on these tests, they do tend to do that. They will drop in one of these particular line segments, but then the question they ask will have something to do with properties of one of the other line segments. So it's important to know that in an isosceles triangle, if you find any one of these structures, then you automatically have the properties of all 4 of them. And that's specific to an isosceles triangle, so don't try to apply that rule to a triangle that's not isosceles. Okay, so another thing that we said is looking at these triangles, the isosceles triangle that has one of these structures built into it. We also pulled back in all of our old triangle congruence rules: side, 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 angle, angle, and angle, angle, side. And what we found was that there was enough information between the little triangle on the left and the little triangle on the right to say that those 2 triangles are in fact congruent inside of there. There was enough information for all 4 of those shortcuts inside of this triangle. Okay, so a small way of saying all that is when you have an isosceles triangle and you drop in one of those line segments inside of the isosceles triangle, then you have two congruent triangles that have all kinds of properties swimming around inside of there. Okay, one other little rule that shows up from time to time is this one, and it's called the mid-segment theorem. Okay, and the mid-segment theorem deals with the idea that if you take a triangle, okay, and connect the midpoints of two sides of that triangle. Okay, so like on the left, we figured out where the midpoint is. On the right, we figured out where the midpoint is, and we connect those two midpoints. Then what happens is there is a guarantee that the mid-segment that you just drew in is going to be parallel to that third side that we have not messed with yet. Okay, and that becomes important because if we know we have parallel lines, then that brings into play corresponding angles, same side interior angles, and stuff like that. Okay, so we looked at some examples, and as we saw kind of for the first time in geometry, the diagrams can get pretty complicated. The trick we said was not to focus on the entire diagram all at once, just focus on the small pieces of information in the diagram, look at only what you need, and block out all of the rest of the clutter. Anyway, at long last, that finally brings us to a conclusion on Unit 4. Tons of information in there, lots of rules and properties and things like that. So an incredible opportunity for potential questions to show up coming out of Unit 4. Anyway, that concludes Unit 4. See you in class.